Good morning, everyone. Welcome to the class. I'm very glad to meet all the students here today. So far in this class, we was talking about signal integrity. It included transmission line theory, differential signaling, crosstalk, and ISI. In addition to that, we was discussing the eye diagrams and jitter analysis. Moreover, we was talking about equalizer and preemphasis with the harmful approaches. Now I would like to move on to next subject that is called as power integrity. And at the end of this month, I'm also gonna be talk about ground integrity. So these three are important and core subject of the class in this semester. In addition to that, we are going to talk shortly about EMI. Now in this week and next week, I'm going to talk about the basic principles and understanding for power distribution network impedance and design. So in conventional circuit design classes, we are not talking about power supply circuit design very details, especially for very high speed, fast switching digital circuits. But in real semiconductors and computers, PDN impedance control is very important subject to guarantee reliability of your systems and to improve performance of your system. So today, I'm going to give you overall view on power distribution network designs. Let me start with simultaneous switching noise. When our driver are switching from 0 to high level or high to 0 level, we have to supply the current from the power supply, and same amount of return current has to come back. That is based on the charge conservation principle and kilovolt voltage current conservation principle. As far as we are sure that our circuit size is very small, this circuit theory will be true. But later, next week, sometime in this class, I'm going to talk about different stories. But still, instantaneously, power supply circuit has to supply the switching current, and also it has to bring back the return current. But the problem is that we're always gonna have inductance, interconnection inductance, because your battery system and your device has certain physical distance. If you want to avoid any physical distance, you have to put nuclear plant, probably nanoscale nuclear plant, adjacent to your I/O drivers or your core circuit in your SoC. But even though your power supply or battery are placed as close as your driver circuit within less than 100 micrometer, still it has inductance. So when we were designing signal integrity lines, transmission lines, we are designing transmission line impedance to be balanced around 50 ohms by balancing capacitance and inductance of your transmission line. So by controlling the amount of electric field energy and magnetic field energy, we can achieve 50 ohm. 50 ohm is a kind of cross-sectional balance. However, in power supply circuit, we have to minimize the inductance. But surprisingly, 100 micron distance is still our problem. Why inductance is so important? Because in the high-speed digital circuit, we have switching current divided by switching time. Because our current is increasing because our system integration is becoming higher and higher, and our switching time is becoming sub-nanosecond. Now it is approaching to picosecond level, and in the long future, it could be in 100 femtosecond level. So this dt divided by di divided dt is going to be extremely high. The only solution we can minimize the simultaneous switching noise is reducing L. As I mentioned before, even 100 micron length is our problem. So the only way we can overcome this is that number of interconnections should be more than 1,000. Then average inductance will be around 1,000 times. It will be divided by 1,000 numbers. That's why number of interconnection in semiconductor on-chip level or off-chip level, the number of interconnection is becoming extremely high because one reason is that we want to increase the bandwidth of interconnection. Second thing is we want to minimize the power supply noise. The only way to do that is to reduce the inductance, and effectively we can reduce that by number of interconnection. That's why I keep saying that number of interconnection in your semiconductor and computer system will be more than millions or more in the near future. This is the nature. This is not an engineering principle. This is physics principle. For example, let's calculate a little bit. Let's assume that switching current is 100 amps, including core and I/O. And let's assume switching time is 10 picosecond. And let's assume that inductance is nanohenry level. Usually, if your interconnection length of power supply circuit is centimeter level, it is usually a 10 nanohenry level. If your interconnection level is about millimeter, I remember it is usually a nanohenry range. So this is not long distance, assuming you have voltage regulator module at PCB and you have switching devices inside your chip. So usually power supply is outside of your chip. So your semiconductor chip size is more than centimeter by centimeter. So nanohenry inductance is very typical number of interconnection. Then if you multiply L dt, L is 10 to minus 9 nanohenry and 100 amps and 10 picosecond switching time, and then it is becoming 10 kilovolt. This is very rough calculation. I may make some mistake, but the meaning of this number is right. I'm very sure about that. So you assume that you have 1 volt power supply for your digital chip, and surprisingly, if you are switching 100 amps with 10 picosecond switching time, you're gonna generate kilovolt switching noise. So it's becoming really high power amplifier RF circuit. So in order to bring it down to millivolt level, you have to reduce the effective inductance in a femtohenry range. That will be corresponding to distance of less than sub-micrometer. It is physically impossible. That is why I'm keep saying that semiconductor system has to be three-dimensional, so that you can put battery underneath of your chip, and your circuit is just over the wafer. Then if you thin down the wafer thickness, you're gonna minimize the inductance, and you can increase number of power inductance. So in order to go to femtosecond range, probably number of interconnection here should be probably more than 10 to 3. So at the end of this slide, my conclusion is that simultaneous switching noise reduction and design is a range of art, not the engineering, because we have to fight against extreme physics. We usually assume that power supply line voltage is constant voltage, but actually it has some oscillations, and probably the peak-to-peak value will be determined by LDI/dt, and the frequencies of this oscillation is coming from resonance. Resonance says in PDN. So in this class, we are going to talk about resonance of PDN and L control. Those are the main subject of class in this week. One approach to minimize the simultaneous switching noise is, I would say, is hierarchical PDN network design. Hierarchical means physical level should be hierarchical. Also, frequency of your PDN structure should be hierarchical. So I would like to ask you to remember this hierarchical concept very cleverly in your mind. Let me talk about that approach from now on. Let's assume we have I/O drivers. Typically, I/O drivers are consuming very large switching current. I'm assuming that I/O interconnection could be transmission line or capacitive load. If the interconnection length is very short compared to wavelength, we can assume that is a capacitive load. But usually in high-speed interconnections, we have to consider it to be a transmission line. Switching transition has to propagate at the speed of light. If the impedance is not well matched, it will suffer deflections. When this switching current is propagating along the transmission line, please remember that instantaneously switching current and return current will propagate with the speed of light. And this current has to come from power supply network. And return current has to come back. And shortly, I'm not going to go very deeply about this current issue because I don't want to make you very confused. So this switching current, return switching current has to go back to decoupling capacitor. What I mean is that capacitor is a kind of short-term battery. What I'm saying is that capacitor is becoming fast switching battery because decoupling capacitor can store charge for supply current and return current. So usually inside the chip, we are putting on-chip decoupling capacitor. Inside chip, so it's gonna be less than 1 centimeter distance. We are putting the decoupling capacitor inside the chip. And usually this on-chip decoupling capacitor has minimal inductance because of a short distance, and it has minimal parasitic inductance. It is responsible for more about gigahertz range and switching time of 10 picosecond, and distance should be less than millimeter. I'm saying that we have to approach with hierarchical design. If we have infinite amount of on-chip decoupling capacitor area, probably we don't need to have this hierarchical design. But inside the chip, we can have only minimal amount of capacitors because of area limitation. So, however, advantage of this on-chip decoupling capacitor is that it has minimal inductance. So switching noise could be very minimal. And later on, we will tell you that resonance, self-resonance frequency is gigahertz range. So this on-chip decoupling capacitor is responsible for charging and discharging current at high frequency range. Let's assume in the future, in the near future, you have iOS driver inside your chip who has around gigahertz, over 10 gigahertz data rate and less than 10 picosecond switching time. You have to put huge amount of on-chip decoupling capacitor, and this on-chip decoupling capacitor will work as a fast switching battery. Without it, your chip will be in serious problem because power supply noise will be huge and it will be conveyed to I/O jitter. That jitter is called as power supply induced jitter, PSIJ. And sometime next week, we're gonna go back to that issue. So to minimize the PSIJ, you have to put good amount of on-chip decoupling capacitor. Why we have to put probably 20 and 30% of your chip with the capacitor? Because we want to have stable power supply network inside the chip. What is the advantage of your on-chip decoupling capacitor? Because it's placed very close to your I/O switching circuit, so inductance will be minimal, and you can minimize power supplying circuit noise. For example, let's assume that if you are supplying this switching charge inside chip from off-chip battery, distance from your battery to battery or VRM, if the battery and your I/O driver distance will be more than centimeter, and that amount of distance may not be acceptable for very high frequency switching. This battery may be more useful for kilohertz range switching. Kilohertz range in digital circuit is very rare. Probably this battery is more suitable supplying the charge to the on-chip decoupling capacitor. Also, you can put on package decoupling capacitor, and it may be responsible for switching current of 100 megahertz range and picosecond switching time, and distance might be around 1 centimeter range, and inductance could be nanohenry range. Here, inductance could be picohenry range. So if your I/O circuit or core circuit has certain amount of switching current in 100 megahertz range, you have to be carefully responsible for designing of on-chip decoupling, on-package decoupling capacitors. Somehow, this current will be responsible for charging and discharging around 100 megahertz. Also, some of this current will discharge your on-chip decoupling capacitors. Or in addition to that, you have to put good amount of on PCB decoupling capacitors, and this capacitor will be responsible for megahertz switching current and nanosecond switching current, and distance might be 10 centimeter range from your I/O circuit to on-chip decoupling capacitors. Now, I would like to summarize this slide by saying that, number one, our power supply network is not ideal. There's no ideal power supply network. Ideal power supply network has to have zero impedance. That means we have to have zero inductance, but that will be never possible. In addition to minimize the inductance of power supply network, we have to put decoupling capacitors. Capacitance between power network and ground network serve as charge tank. It supplies the charge, switching charge, and it brings back to the return current. So you have to, we may have, number three, we may have very different type of decoupling capacitors. Sometimes we are putting decoupling capacitors inside chip, or sometimes on package, on PCB, or on VRM. Number four, they are placed at a different separation, different distance from the I/O circuit. The best is to put infinite amount of decoupling capacitors as close as possible, but physically it is impossible. So we are approaching hierarchical decap design. On-chip decoupling capacitor has minimal amount of capacitance because of area limitation of your semiconductors, but it is very close to the I/O or core circuit. So it is more responsible for very high frequency switching current because it has self-inductance and capacitance, so it has self-resonance frequencies. As shown up in this slide, it's gonna have self-resistance and self-inductance. So on-chip decoupling capacitor has minimal resistance and inductance and a moderate amount of capacitance. So resonance frequency will be very high, and so it will be more responsible for gigahertz range switching current. As we have mentioned many times in the class, we're gonna have many high frequency, number of I/O will be increased, data frequency will be increased, so switching current will be huge at high frequencies. So we're gonna have to put more and more on-chip decoupling capacitors. Probably if this is your chip, probably 50% of your chip will be covered by on-chip decoupling capacitors. Why we need to do that? Because we have to put we want to minimize the switching noise. Otherwise, logically, zero and high cannot be defined. I diagram will be hugely distorted because this noise will be coupled to the I/O interconnection. So we cannot achieve very high frequency or high data rate with this switching noise. So that's why in the long future, probably main area of your chip is gonna be covered by on-chip decoupling capacitors. But there are certain limitations area of your chip to put decoupling capacitors. So next, alternative design of on-chip decoupling to minimize the on-chip decoupling capacitor will be on-package decoupling capacitors. So we have to cleverly design the package structures to add some decoupling good amount of decoupling capacitors, and number of interconnections should be very large. In this slide, I'm giving you an idea and basic concept of hierarchical power distribution network design. This hierarchical is very important concept with respect to physical design and frequency allocations. This is also very important slide, and we're gonna come back to this. This is a kind of overview. This is, I think this is a conceptual overview of the decoupling capacitor design and power distribution network design. And this graph is conceptual design of your PDN power distribution network with the concept of impedance curve. Let's take a look at this slide one by one step by one step. We want to have ideal PDN impedance. Probably that should be less than micro ohm or nano ohm in the long future. Probably some chip probably it should be less than milli ohm. As I mentioned in the previous slide, 50 ohm is very easy number. That is very close to our nature of interconnection, but this is against the nature of very extremely small. In our life, every day we have good things, 50%, we see happiness at 50% of our time, sometimes stress and unhappiness 50% of time. At the end of each day, if I feel that I have 50% of happiness and 50% unhappiness, I'm okay. Sometimes I have 51% happiness and 49% much happier. Then in 365 days, it's gonna be 365% increase of happiness. That is almost impossible, but over the weekend, I had good messages from my old students, and also I met my friends, and I had a good weekend with my family. So that a good part of my job, my life. A little bit unhappy part of my life over the weekend was that I had business golf, and business golf is not that happy. Golf with friends and fun is good to me. Combining fun with a business seems not be the best case. So over the weekend, I have 50% happiness and 50% unhappiness. So that's good. But so that's why I think 50 ohm impedance matching is beauty of our interconnection design. But when we are designing PDN impedance, we are being pressured to be happy for 99.999%. Psychologically and biologically, it is impossible unless we have a drug or cocaine. So this is very unnatural, but what I'm saying is that our target impedance of power distribution network is nearly a very small impedance from DC to gigahertz, or it could be later on 100 gigahertz. So very broad, these are very difficult tasks with respect to two different point of view. Number one is that very low impedance we have to achieve that is against our physics. Second one is we have to achieve that from DC to 100 gigahertz. It's gonna be very difficult. That is first thing I would like to emphasize at this moment. Second observation here is I would like to very empathically stress to you is that it's gonna go constantly at a higher and higher frequency range because of inductance. This inductance is coming from power via trace, plane, and sometimes your decap also has equivalent serial inductance. So any type of interconnection in your power supply network are causing this inductance. Because of inductance, impedance will increase because J omega L. But you remember that we're gonna have huge amount of switching current in gigahertz range, and naturally the impedance is much higher than our target impedance. And it's gonna be a source of SSN, and it will produce EMI, or sometimes it is producing the PSIJ issue, power supply induced jitter. If you are violating the EMI spec, you cannot sell your system or your semiconductors. Your customer will be complaining. And if you have too much PSIJ, you cannot meet the performance of your computer system, especially for machine learning or metaverse computers. So first message I'm trying to tell you at this moment is that we have to engineer our PDN system to be close to ideal PDN impedance. The first element that is making us very hard is the inductance of interconnection. Third part, I would like to show you is that if you add Onchip decoupling capacitors, you remember that impedance will come down. You remember that if you add capacitance in your power supply, so inductance is really making the impedance higher and higher. That's really the problem. But capacitance, including decoupling capacitor, really will bring it down the impedance. The impedance, which is caused by capacitance, is J omega C, 1 over J omega C. So if you add capacitance inside chip, impedance will bring it down. But however, if you have certain resistance inside your chip, because inside the chip, your interconnection is very thin and narrow, so it's gonna have resistance. And now again, at over 10 gigahertz range, it is gonna go back because of on-chip inductance. This green curve is actually the purpose of on-chip decoupling capacitors over gigahertz range. Without on-chip decoupling capacitors, your inductance impedance will steadily, continuously increase because of inductance of your whole system. This inductance is coming from PCB, package, and on-chip. All of them will be added together to constitute this inductance. Now I'm trying to explain the concepts of hierarchical PDN with impedance curve. Initially, in PCB, you have bulk capacitance at VRM. It is responsible for filtering the high frequency noise and supplying the charge at kilohertz range. So it is good to bring it down the impedance at kilohertz range. And at the PCB level, also you are adding capacitance. And because of the PCB level capacitance, your impedance will coming down and coming down. And eventually it is following the inductance curve. Also at the package level, you are adding some capacitance. Later on, I'm going to show you that. Also, you're gonna add some resonances. And here, even though I'm not going to show you very details, if you have PCB planes, it's gonna create another resonances. These are the feature of PDN impedance curve. So by engineering bulk decoupling capacitor at VRM, you have in megahertz range, if you wanna reduce the switching noise, you have to control the PCB level decoupling capacitor designs. In megahertz range, you may have to control the package level decap. In the 100 megahertz range, if you wanna control the EMI levels associated with the power supply network, you have to control the PCB level plane resonances. If you have PCB level multi-layer PCB, it's gonna create the resonances. Here we have inductance and capacitance coupled together, we are creating the resonances. And inside the chip, we're gonna have low impedance, but eventually it is going to go to an high impedance because of on-chip interconnection inductance. Interconnection means via trace and power planes and so on. So this is the end of my explanation with the hierarchical PDN impedance concept. Yunjiwon, are you there? I saw you sleeping overnight, studying overnight today.
네, 교수님.
요 페이지 한번 설명해 보시겠습니까?
이제 앞서 교수님께서 이제 simultaneous switching noise SSN에 관해서 설명을 해주셨는데, 이 SSN이 이 I/O 드라이버에서 스위칭 커런트가 발생함에 따라 온칩, 패키지, 그리고 PCB, 그리고 배터리, VRM 레벨까지 이제 리턴 커런트가 전부 흐른다고 말씀을 해주셨습니다. 그래서 이 과정에서 이제 이 hierarchical PDN 임피던스를 맞추기 위해서는 이제 이 PDN을 이상적인 PDN은 0ohm의 수렴을 하게 되는데 이제 이렇게 회로상의 인덕턴스 또는 기생 성분들을 위해서 이를 맞추기는 거의 불가능한 것 같습니다. 따라서 저희가 PDN을 설계함에 있어서 이제 최대한 임피던스를 낮추고 이 넓은 대역폭에서 이를 맞춰야 되는데 이를 분석함에 있어서 계층적으로 이제 온칩에서는 기가헤르츠 범위, 패키지에서는 메가헤르츠, PCB와 DRM은 각각 킬로헤르츠 단위에서 각각의 디캡을 설계를 해야 합니다.
네, 맞습니다. 또 하나 강조하고 싶은 거는 이제 로컬 배터리를 만들기 위해서 디커플링 캐피터를 설치하는데 무한대의 왕창 디캡을 설치하면 좋은데 물리적으로 불가능하고 너무 비용이 비싸고 그래서 이제 인덕턴스를 설치를 하면 주변에 디캡을 설치하면 주변에 인덕턴스하고 공진을 일으켜요. 하이 프리퀀시 공진을 일으켜서 이런 포인트에서 임피던스가 팍팍 높아지는 거예요. 예를 들면 이런 점에서 공진을 어떻게 컨트롤하는. 그래서 이 인덕턴스 때문에 올라가긴 하는데 어떻게 하게 부분적으로 떨어뜨리냐. 자기가 전략적으로. 그 다음에 부분적으로 떨어뜨리기 위해서 디캡을 설치하는데 자연적으로 생긴 인덕턴스와 만나서 공진을 일으켜. 이게 또 사고를 쳐서 공진은 우리가 또 제거할 수는 없기 때문에 피해가는 거다. 이런 말씀을 드립니다. 그런데 이제 그러면 이 PDN을 어떻게 얻느냐, 시뮬레이션으로 얻느냐, 측정을 통해서 얻느냐인데 사실 이거 다 체결해서 측정을 할 수가 없죠. PC부터 G까지. 그래서 시뮬레이션으로 많이 할 수밖에 없겠습니다. 자, 그래서 이제 파라스틱스와의 싸움이다고 이렇게 볼 수 있는데 신호선은 전송선이니까 웨이브만 잘 흘러가게 하면 되는데요. 거기도 이제 로스가 있어가지고 이제 그 자연 현상을 부딪히는 건데 스키니프톤 다이렉트 그래서 이퀄라이저나 뭐 이런 게 있는데 여기서는 조금 더 극단적으로 싸우고 있는 것 같습니다. Thank you, 지원. 지원, are you still there?
네, 교수님.
How did you study overnight? Do you have some homework or projects and how did you do that?
밤을 샌 건 아니고 아침에 일찍 일어나서 새벽에 일찍 나왔습니다.
그거 보통 노인네 현상인데. 네, 알겠습니다. 네. So this is written expressions about the hierarchical PDN. Number one, when we are designing the hierarchical PDN, we have to design the frequency-dependent charging current and return current loop. And also, we have to put our network design is location-dependent. Ideally, we want to put infinite amount of decoupling capacitors as close as possible, but we have to put some hierarchical design. Later, not now, I'm going to talk about the switching current supply will be also limited by speed of electromagnetic wave. In the previous slide, when I was talking about power distribution network, I was relying on capacitance and inductance circuit model. But from here to IO circuit, even though you want to supply the charge as fast as possible, it will be limited by the speed of light. What I'm saying is that charging current is also electromagnetic wave. This is a little bit different concept, but in my view, this is very distal current and this current will be transmitted as a form of electromagnetic wave. And sometime next week, I'm going to talk about this theory. Many times in this class, we are having device concept and circuit concepts and electromagnetic wave concept. We have to combine three of them together, especially over charging and return current over gigahertz range. We have to apply the electromagnetic wave concept. Then limit by loop inductance is eventually limited by inductance. And so because of that, we need to have hierarchical decoupling capacitor design, and our ideal PDN impedance will be zero impedance. I'm not going to go very detailed about this subject because this will make you very confused. Depending on charge on discharging loop, current loop will be different. And for example, when you want to minimize the switching noise when you are switching from 0 to 1 level or from 1 to 0 level, PDN design methodology will be a little bit different. Overall, it will be okay, but different because current loop of charging and discharging loop will be different. But I'm not going to go very deeply into that. So as a summary of the class so far, I would like to mention about difficulties of PDN designs in high-speed digital circuits. I sometimes told that power integrity might be 3 times more difficult than signal integrity. And number one is it's not shown in the textbook. What I'm saying is in the digital circuit book, at least we have to allocate a chapter about 30 to 100 pages to describe about the PDN design. Because without stable power supply, we cannot define digital 0 or 1. So we cannot design the PLL or flip-flop circuits or combinational circuits or ADC or DAC. But the textbook does not include any knowledges or experiences or principles about the power supply network design. So second difficulty is that we haven't considered in circuit design. And number third is that especially inductance and resonance and some part of C in power distribution network is coming majorly from parasitics. So it is not shown up in the circuit diagram. Let's assume you have decoupling capacitors. Up to certain, the model of decoupling capacitor may be like that. It may have equivalent serial inductance and capacitance. Because of resonances, F0, after resonance, the behavior is dominated by this L, parasitic L. Below this resonance, the impedance is dominated by capacitance. And this resonance frequency is usually about 110 megahertz. Even though the shape of your decoupling capacitor is a capacitor shape, and in the circuit diagram, it is shown up as capacitor. But unfortunately, it is capacitor only at below resonance frequencies. In the gigahertz ranges, it is very, very difficult to find a capacitor because inductance is more dominant. Probably Onchip decoupling capacitor is good at gigahertz range capacitor, but it usually has certain amount of resistance. So resistance is becoming very dominant at high frequency because of skin effect loss of device and interconnections. So in PDN design, circuit diagram doesn't help much. You need to have very clever high frequency model you need to have. And number 3 difficulty associated with the PDN design is parasitic is more dominant than object itself. Also, in some part, we have to be involved in wave properties. Power is delivered in a form of electromagnetic wave, and this wave likes zero impedance. In transmission line, the line likes 50 ohm impedance, which can carry high-speed distance signaling, but in power supply network, electromagnetic wave prefers zero impedance transmission line. 50 ohm transmission line usually has this kind of shape, but zero impedance line has very thin Ångström level and area should be infinite. Inside this transmission line, wave will propagate in this direction and in this direction. So the very difficult part of this power supply network is that we have to consider wave property, power wave, not signal wave, power wave of 100 amps. 100 amps current is propagating or delivered to your digital circuit in a form of wave. You have to design the transmission line of 0 ohm. That is very difficult. High current and high frequency wave. Also, it is position dependent. We have this kind of impedance curve, but I'm saying it is position dependent. What does that mean is if you have PCB, if you have CPU, and if you have DRAM, depending on the position of CPU and DRAM, DRAM may have different impedance and CPU may have different impedance curve. You remember that in transmission line, length is controlling the skew and delay when we are sending very high frequency signals. So length combined with frequency, speed of light is controlling the delay, and in some part of the waveform of high speed distal at the receiver side. And likely PDN impedance is also position dependent. That is not usual concept of circuit designs. I think number 1, number 2 is important, but parasitic is more dominant. And also we have to consider power properties. And it is also depending on the position. So let's assume that you are designing a computer with Intel CPU and Samsung DRAM. 2 different companies are designing 2 different computers with 2 different PCB designs and package designs. Company A has smaller SSN and less EMI and less PSIJ, but company P may have higher noise. That is the power of engineering comparison between the 2 companies. And I think this number 3, number 4, or number 5. So one example is that one company designed a position of CPU with minimal noise position, while the other company doesn't care about that, when probably their PCB art designer or package designer did their design in their own way. Number 6 is it's extremely difficult to design ideal PDN, and also various types of resonances. We have to control the resonances. Number 8 is, I think, cost is really high. To overcome number 3 to number 7, we have to minimize the resonance inductance and has to put as close as possible. And we also have to put good amount of engineering resources on power integrity when we are designing PCB and packaging and chip together. And even though I'm not showing you very well, in this area, there are some interactions between on-chip circuit level and off-chip circuit level. You see that inductance is majorly coming from off-chip PCB and packaging, but on-chip capacitance is majorly coming from on-chip decoupling capacitor. Here we have another resonances. Even though you are designing your PDN circuit very well, if you are just doing your job at the PCB level or packaging level, you cannot control these resonances because it is combined by on-chip interconnection, on-chip decoupling capacitor, and off-chip inductance. So the last difficult part of a PDN design is that PCB engineer, packaging engineer, and chip engineer, sometimes EMI engineer has to work very closely together because there are some interactions at the boundaries. So if we have SSN, simultaneous switching noise, let's assume that because we are not properly designing the power supply network, usually at these resonances, we have four different type of resonances here. Probably we're gonna have PCB level resonances, package level resonances, and PCB plane resonances, and resonance by off-chip inductance and on-chip capacitance. And these resonances, if that around that resonances, we're gonna have large amount of switching noise. And if you do the Fourier transform, we're gonna have certain EMI peaks. And it will create the radiations. And because usually a power line has some area like this, 50 ohm line impedance is very thin line, but power line has to be very wide. Why to do that? Because to reduce the impedance, so it's gonna be an antenna. So we're gonna have large amount of antenna trace via plane and edge about of all PDN network could be an antenna. Whole your interconnection system could be antenna. Also, this noise could be coupled to RF circuit or analog circuit or sensor circuit. This coupling could happen at via plane and traces. Also, this noise can be coupled to I/O power, and it's gonna create the jitter. So reduction of voltage margin and reduction of timing margin, and eventually jitter will increase. This is gonna be end of class today. On Wednesday, I'm going to talk repeatedly again and again on this subject. Originally, I was planning to have more than 20 slides to talk about, but I don't want to give you all of them in a class. So I will come back again and talk about repeatedly again. I'm going to talk about this slide. Jihun, are you there? I saw you in 7 o'clock in the morning in the laboratory. Jihun, are you still alive? Or Sangwoo, are you there? Okay, let me finish one more slide here. Now, so far, I was talking about the PDN impedance design. It may have certain resonances, higher frequency resonances, and it may go back again, something like that. This is PDN impedance. Let's assume that your core or I/O circuit of your chip has current spectrum. It may be a harmonic frequency of your clock. If some of your current spectrum is same frequency as this resonance frequencies, you're gonna have, because impedance and current will be a voltage, and FFT of that voltage is gonna be this curve, and we're gonna have huge EMI peaks here. So when you want to solve this EMI or some problem, you have to know what is your PDN impedance, and also you have to have some certain amount of information about the current spectrum. And by multiplying that, we're gonna have some frequency, high peaks, noise peaks at certain resonance frequencies of PDN. So in order to avoid this high frequency EMI peaks, you have to redesign the PDN. Sometimes there are two different ways. Number one is you have to redesign PDN impedance by having different inductance and capacitance. Second approach is you have to redesign the current spectrum by changing the clock frequencies and so on. And so you have to avoid overlap of this resonance peak, high frequency resonance peaks, and current spectrum. Let's assume that unfortunately you have two peaks of EMI. In the time domain, you're gonna see that it has some ringings. We are assuming that our ideal voltage is a constant voltage, 1 volt, but actually it's gonna have some certain ringings. And this high frequency period of this ringing is related to from this low frequency EMI peaks, and small ringing of this EMI is responsible for this high frequency peaks, and these are coming from the resonances. 자, 여러분께 이 슬라이드를 보면서 한번 또 정리해 보겠습니다. SSN이 생기면 무슨 문제가 생기냐? 당연히 전압이 흔들리니까 이 흔들리는 소스에다가 패턴이 있으니까 이게 안테나가 돼서 전자파를 방사시켜서 주변의 RF 시스템의 성능을 떨어뜨립니다. 그러니까 이런 패턴이 들어가 설계를 하면 핸드폰의 통신 수신 감도가 떨어지는 거죠. 또 하나는 안테나가 아니라 가까이 있는 구조로 전파되는 걸 커플링이라고 하는데, 이제 비아도 있을 수 있고 플레인도 있고 트레이스에서 RF 서킷 트레이스나 아날로그 서킷이나 센서를 이렇게 커플링이 돼서 이들의 그 성능을 떨어뜨립니다. 또 하나는 IO 파워로 또 전달이 돼서 I 다이어그램이 이렇게 지터가 생기고 I 다이어그램이 디스토션 생기는 게 이렇게 생깁니다. 그러면 디자인 입장에서 보면, 아까는 현상을 계속 해석을 했는데요. 디자인 입장에서 보면 우리가 PDN 임피던스가 주어지면고 거기에 전류 스펙트럼이 흐르면, 특히 공진 근처에서 임피던스가 높기 때문에 그때 근처의 전류 스펙트럼이 딱 EMI 스펙트럼이 된다. 그래서 이 EMI 스펙트럼을 해결하고 싶으면 공진 주파수를 왔다 갔다 하게 하거나 커런트 주파수를 왔다 갔다 하게 하도록 디자인을 바꿔야 되겠습니다. 근데 만에 하나 이런 피크가 있다라면 파워 서플라이 노이즈의 메인 노이즈 주파수와 서브 노이즈 주파수가 다 바로 이 SSN의 EMI의 피크의 크기와 위치에 의해서 좌우되겠습니다. 제 생각에 오늘 강의가 앞으로 2주간 강의의 전체 오버뷰를 보여드렸습니다. 이제 수요일부터는 조금 더 깊이 지금 여기 보면 여기 다양한 피처가 있잖아요. 임피던스에 이 피처 하나씩을 들어가서 여러분들한테 소개해 드리겠습니다. 여러분 25명이나 들어오셨는데 채팅도 있네요. 오케이. 지훈이도 있네요. 오케이. 그래요. 지훈이 지금은 있어요? 네, 네. 그럼 이 페이지 한번 설명해 보실 수 있으실까요? 아, 마이크가 안 돼서. 오케이, 알았어요. 자, 오늘 여기까지 강의하겠습니다. 지금까지 수업에 들어오신 윤지원, 김경무, 경민, 최경민, 김예원 학생, 현우, 준영이 안 줄고 있네. 준상이도 안 줄고 있네. 준상이 이 페이지 한번 설명해 봐. 네, 네. 한번 설명해 볼래요? 오늘은 마이크들이 잘 안 되는 것 같아요. 예, 정현,
들리시나요?
예, 들려요. 한번 말해 볼래요? 설명해 볼래요? 준상의 목소리로?
이쪽에 나오듯이 이 오실레이션이 SSM에 의해서 일어나는데 이 볼티지 피크점들이 어, 특히 임피던스의 이제 임피던스 그리고 커런트의 이제 곡도로 나타내게 되어서 이 특이 임피던스의 공진점들을 좀 조절을 해서 네, LC 값으로 특이한 공진점들을 조절해서 이 볼티지 피크를 좀 낮출 수 있다라는 말씀을 해드렸습니다.
네, 그렇습니다. 그래서 우리 수업은 주로 PDN 임피던스를 어떻게 제어할 거냐 초점을 맞추겠지만 하여튼 실제적으로는 두 가지 어프로치가 있다. 커런트 스펙트럼을 바꾸는 거하고 임피던스를 바꾸는 거하고. 근데 생각보다 이 문제가 좀 심각합니다. 오늘 수업에 들어오신 박건희 씨, 조인수 씨, 장우진 씨, 장서희 씨, 신유한 씨, 정학천 씨, 이규아 씨, 최문재 씨, 최성구, 그 다음에 정희조, 장영민, 조세영, 나종우, 홍종현, 이정현, 문준영, 김현우 3명은 카메라까지 켰네요. 김혜연, 김경민, 윤지원, 박준상 모두 감사합니다. 즐거운 하루 되시고요. 수요일 날도 약간 이렇게 철학적으로 더 얘기하겠습니다. 다음 주에는 좀 깊이 들어가지만 이 전체 여러분들한테 PDN 설계에 대한 개념을 또 말씀드리겠습니다. 오늘 여러분 수고하셨습니다.
감사합니다.
네.